And like people in the chat, like how many problems were you guys able to solve today? Like that will give me some rough estimate on which problems to focus more on and which we can probably move faster. So I'm planning to discuss all problems except min-max part. Like I haven't really seen how to solve this one yet. So okay, I will start from given problem, give 4 problems first. Okay, this problem says Coldplay tickets. You want to go to Coldplay concert along with one of your friends. You are buying tickets for everyone. Each ticket costs 5,000. Calculate total amount you need to. So you should essentially print like n is your number of friend and 1 is you. So total n plus 1 tickets you need. So you can print n plus 1 into 5,000. This will be the solution for the problem. Moving on to the second problem, it says calorie limit. Sushil is a diabetic patient. He is only allowed to eat at most 3 calories. However, he likes to eat sweets a lot. There are n sweets in front of him. The ith sweet has calorie amount of count of AI. Sushil will eat the sweets in order. That will he will start from sweet 1, 2, and such on. If eating the ith sweet would take him over his daily count, he will not eat it, and he will also not eat any further sweets. Find the maximum number of sweets Sushil can eat without existing the calorie. So here the idea is like we will read all the integers as input n, k, and all the elements of the array. Then we will maintain like how many more calories we can eat. Whenever we encounter some food which has more calorie than whatever we can eat now, we will break it. Otherwise, we'll remove that, subtract that from more total calories we can still eat, and we will keep continuing the same. So yeah, let's first read the number of test cases as input. And let's also read the number of k as input. First, you should ensure that you read all the integers. Like this is one of the mistakes where people will just stop reading after taking all the inputs. This will end up being the solution for the second problem. Third problem says add 1 or 2 game. Alice and Bob play a game. There is an integer x which is initially 0. On their turn, Alice and Bob can choose to increment x by 1. The game ends as soon as x is greater than or equal to n holds. Whenever the game ends, Bob wins if x equal to 1, otherwise Alice wins. Alice goes first, players alternate. If both the players play optimally, predict the winner. Okay, this looks a bit interesting. So, like, any ideas on how do we go about solving this one? Like, okay, n is up to 10 only. We can essentially even brute force it if we do not want to know, like, who wins. Or, like, basically, we know that Alice x greater than or equal to n game ends. Bob wins if x equal to n, right? So, if x let's probably just try some guesswork here. Okay, people in the chat says only for n equal to 1 Alice wins, otherwise Bob always wins. Let's try to see why that is the case here. So let's start looking at values from n equal to 1 is equal. If x equal to n, Bob wins, otherwise Alice wins. Okay. So whenever n is equal to 1, it's Alice's turn. He can directly do +2 and win over here. So like you can see why like Alice will win if n is equal to 1. Let's see what happens if n equal to 2. If n is equal to 2, then if Alice does +1, in that case the game has not ended yet and Bob can do a +1 to reach equal to 2 again. If Alice does +2, game just ends there, and in both the cases you can see Bob wins. Now let's see what happens if n is equal to 3 VF. Alice has two choices. We start from 0. Alice does a +1. Alice does a +2. In this case, Bob can do +1 to reach 3. In this case, Bob can do +2 to reach 3. So again, Bob will. Let's see what happens when n equal to 4. If Alice does +1, and here is the case when Alice does +2. In this case, Bob can do +2 to reach 4 total, and Bob can win. In this case, what Bob can do is he can again do a +1. So we now have a 2. And now the game is equal to like it's again Alice's turn, and we have only 2 numbers left. 2 more left, and we can see like here the game is Alice's turn, and if 2 is more added over here, then Alice will win, otherwise Bob will win, and this situation is exactly same as n equal to 2 test case right now. Like the same things will happen. So it looks like for n equal to 1, Alice wins. For n equal to 2, 3 and 4, Bob wins. And people in the chat claim like Bob will always win, but can we try to prove it? Would be another interesting question, like why is it the case? Let's probably say like proof by induction. Let's say now we want to know for n greater than equal to 5 who wins. And our hypothesis is one, Alice will win, and otherwise Bob wins. So let's say we know that 1, 2, 3 up to n minus 1. Here Alice is winning, and here like if it's Alice's turn and these are the number of stones remain, then Bob wins. And we also know that n is greater than equal to. Now if Alice plays, we start with 0 first. If Alice does a +1, we reach at 1. If Alice does a +2, we reach at 2. Now what we can see is like in this case, Bob can do a +2 to reach 3 here. In this case, Bob can do a 1 to reach total +1 to reach 3 here. And the game will be equivalent to n minus 3 case, assuming for the case whenever n is greater than equal to 5. And like for cases when n is greater than equal to 5, let's play it this way. If Alice does +1, Bob will do +2. If Alice does +2, Bob will do +3. So now we need n minus 3 more, and from here, as long as n is greater than equal to 5, this should be the strategy. And you can see like if n is greater than equal to 5, n minus 3 would also be greater than equal to 2. And in this case also Bob is winning. And like that is essentially the point here. we can keep subtracting 3, 3, 3 as long as the resulting number is greater than equal to 2 here. Only when n equal to 4, we should probably play with this strategy. And probably n equal to 3 and 2, we have already seen what should be done. And this way we can always ensure that in 2 turns, both again Ali's turn will come and we will keep subtracting 3 until we have a number between 1 to 4. And in that case, we have already seen who the winner would be. Like 4 will ensure that we don't do a -3 again to reach 1. So we will always end up with 2, 3 and 4, and in every case Bob is winning. And essentially this ends up being the solution for this problem. Any questions on these 3 problems first before we move on to D1 problems? Okay, now moving on to D1 problems first. I am planning to discuss these 4 problems. So let's see. Let's start with GCD. You are given an array A of size n. You can perform following operation as many times as you want, possibly 0. Choose integers L, R, and X and do one of the following operations. For all I between L to R, set AI equal to AI XOR X. And for all L to R, set AI equal to GCD AI comma X. That is, choose a subarray of A and integer X and either replace every element of subarray with the GCD with X or replace every element of subarray with virtualized XOR with X. Compute the minimum number of operations required to make all the elements of array equal to 2. So the problem statement says we have been given an array. We have to choose some L to R here. And then we can replace every element with AI XOR A, XOR X, or we can replace AI equal to GCD of AI comma X. And now we have to make every element equal to K and minimum number of operations required. So any ideas, anyone? Or like probably like any way you people see like to just do it in minimum, like what is the minimum number of moves you can probably do without dealing with a lot of cases? Yeah, like minimum number of moves, like 0 may not always be possible, right? Yeah, like Andrew is right. What we can do is like we can first replace to take the complete array. First, in one step, we can do L equal to 1, R equal to N, and X equal to 1. So that every number becomes 1 now. Because GCD of anything comma 1 is 1. So after this step, everything would be 1. Now we can do L equal to 1, R equal to N, and x equal to k XOR 1. We take this as a value there, so that every value is 1 right now. If we take it XOR with k XOR 1, this will turn out to be k. So step 1. Step 1. So these are the two steps which we can take, and we can make everything equal to k in 2 steps. So now this will prove us that the answer is always less than equal to 2. Now the question is, can we do it in 0 or 1 steps? Like if we want to do it in 0 step, everything should already be equal to k. AI should already be equal to k. And like this is the only way to make everything equal to k in 0 steps. And if we have to do 1 step, if we want to do it in 1 step, then there can be 2 ways. Either we take GCD of everything with k. Basically, another way to say is, if we take GCD of everything with k, and if this makes everything equal to k, then we can get it in 1 step. That is one way to equal. Like either we can, like if we have to do any one operation, then either we can do this operation or we can do this operation. And if you want to do this operation, you can notice that GCD of k comma something would be a divisor of k only. So only the best case scenario when we can make everything equal to k would be like when we take GCD with k of the complete array. And if this process makes everything equal to k, then we are good, right? If this makes every ai equal to k for all k, then print 1. And like this is the best case scenario for us. And let's say GCD is not making it, then we have to see like, is there some way to take XOR and make everything equal to that number? Like another way can be like, now we have to find like, is there a range, some range L, R and X? So is that if we do XOR only in this range, then we can get everything equal to k. Like we have now like, let's say A1 up to AN, A1 up to L minus 1. Then we have some AL to R and AR plus 1 up to AR. In this case, like this is how the range looks like, right? Here we will do some modifications. These elements will be equal to k again, and these elements will be equal to k again. So what we can do is like, we can remove all the elements equal to k from last, and then we can also reverse the array, and then we can also remove all the elements which are equal to k at the last. Basically my idea is remove all the starting elements which are equal to k, remove all the ending elements which are equal to k. Now you have some subarray, because you know that this would be the first element which is not equal to k. This is also the last element which is not equal to k. So you would have to do one operation which involves these two elements. And there is no point in doing an operation on the element which is already equal to k. So now we have this as a part again, where we have this AL plus 1, this AL and this AR. None of them is equal to k, or can be potentially equal to k, we don't know yet. But we know that this element is not equal to k, this element is not equal to k. And we have only one operation, right? Because we know that if we cannot do it in 0, 1, we can directly print 2 and call it a day. So now here my idea is like, find a V such that AL XOR V is k, Let's say v1. Let's say this is the one. And now check if you do XOR in this complete range with this v. With this v, if you do a XOR in this range, will you get all the elements equal to k? If the answer is yes, then print 1. Otherwise, you will never be able to make everything equal to k in this range using XOR operation in k. Equal to, using XOR operations in k. We have also seen if we cannot make everything equal to k using a GCD operation, then we definitely need two operations. And this is essentially the solution for this problem. And like I can probably walk you through my solution here. Like, yeah, like essentially what I did was okay, looks like I did a lot of stuff on this one. First thing we can do is like we can make all the consecutive elements unique. So let's say we have an array of 5, 5, 2, 2, 4. Then we can make it 5 to 4. And this is what I am doing it with a.erase unique and all the elements. This function essentially changes. Like 2, 5, 2, 4. Like because we like whenever we are doing a range and like if you see if we are doing an operation with this two, we can also always obviously include this two, and we don't have to print the operations as well. Or if we are doing some operations on this 5, we can also include this 5 as well. So there is no point in keeping an array like. Now if everything becomes equal to 0 in one of, if already is everything is already equal, then in this case we will have size of a as 1 and a0 equal to k. Because like if when everything is equal to v, whenever we remove consecutive elements like this, we will end up with only one element, and we can print k equal to 2. Now my day is remove all the elements from back which are equal to k, remove all and reverse the array and remove all the elements from back again which are equal to k, and reverse again. So this will give you one more array where you have removed all the elements equal to k from starting, all the elements which are equal to k from back. Now the idea is like let's do GCD of all the elements with k and see if it's equal to k. If we can just take GCD of every element with k and we get a k again, then we can directly print 1. Otherwise, based on like the above operation, or probably I would say like let's first even before GCD, let's say only one element remains. Then we can directly print a 1 here. Like we can just convert this element using a XOR operation and call it a day. Otherwise, if we take GCD of every element with k, we get a k, we print 2. Otherwise, we are printing directly 2 here, and this is 1. Like this is XOR operation, because like I have already removed element equal to k from starting or elements equal to k from the ending. And the idea is like if this XOR with v from everything in this range makes equal to k, then this can happen only if all the elements in this range are equal. So instead of manually running a for loop here, you can just check that all the elements from AL to AR are equal in fact. So, and if you cannot make array equal to 0, complete array equal to k in 0 operation, you cannot make complete array equal to k using a XOR operation in ones, or if you cannot make everything equal to k using a one GCD operation, then you can directly print. Now you know you need at least 2 operations. And now we have already proved that how we can get 2 operations. So this ends up being the solution for this problem. Okay, someone asked like, another asked like, how the minimum is 2, we can bring it. My idea is like, first I will choose L equal to 1, R equal to 1 and X equal to 1, and I will take GCD of everything with 1. And now you know that the complete array is equal to 1, because GCD of anything with 1 is 1. Now my next step is, now choose X such that V XOR 1 is equal to K. Like, you can always find a number like this. And because everything is equal to 1, now you can do an OR operation from L equal to 1, R equal to 1 with this type of V. And now everything would be equal to K here. And like, that is the idea. Like, we can always make everything equal to K in two operations by doing first GCD on complete array and then doing XOR operation on the complete array. So like, we don't have to never go for 3 operations. And then we looked at like, how can we take answer equal to 0. Like, 0 was, the idea for 0 was everything should already be equal to K. Only in that case you don't need any operation to make everything equal to K. So print 0. Or now if you have only one operation, then that one operation can either be a GCD operation or the XOR operation. So for GCD operation, my idea was to just look at if we do a GCD operation with K with all the numbers. If we get K, then we know that GCD from L to R with equal to K can give us the required array. So print N. And if that is not the case, then my idea was remove all the elements equal to K from starting, remove all the elements equal to K from the ending. Now we have some part here, and we know that this element is not equal to K, so some XOR operation must involve this. This element is not equal to K, so some XOR operation was also being involved here. Now I can find an V such that if I do XOR of V with AL, I would get K. And then I can just check if this V, and if I do this XOR with V from this range, will I get everything equal to K? If the answer is yes, you can print yes. Otherwise, you can print 2 there. And one observation here was like, this V can make everything equal to K in this range only if all the elements in this range are equal. So that would be another way to do it. So like, why? Oh yeah, you are right. I have already removed the unique elements here. So I don't need a while loop here. Good call out. If A0 equal to K, A dot erase A dot begin, I can just remove the first element. If A dot back is equal to K, I can again remove like, so yeah, we don't really need a for operation as well. So that's how I'm calculating. Like, I was not sure if this would have combined. This is indeed the way, but I wasn't sure like this would compile. Like, sometimes on segment 3, if I remember correctly, this is. Oh yeah, like A dot pop, right? So this ends up being the solution for GCD. Any questions on this one before we move to the next problem? Okay, next problem is count winning subarrays. Arrays is we call an binary array B of size m winning if it can be converted to 111 by repeatedly doing following operations of finite number. So it says like we have been given a binary array. Binary array means all the elements are from 0 and all the elements are either 0 or 1. And we can do the following operation. Pick one, pick some L and R in the given range such that number of ones in that subarray is strictly more than number of zeros in it, and then replace every element in that part with 1. Given an array of size n, count the number of winning subarrays of A. So the problem statement says we call an array winning if we can make everything in that equal to 1. Like for example, we have this element. And what we can do is in one operations we can 0, 1. Let's say this is our array. Like we can choose any subarray which has number of ones more than number of zeros, such as this is one possible. And now we can make everything equal to 1 here. This will become 1. This will become 1. Now in the next step, we can again choose this array because number of ones here are more than number of zeros, and this can be converted to 1. And now everything is 1, so the answer is yes. We have been given an array A1, A2 up to AN, and we have to count the number of subarrays which can be make winning sub, which we can make winning subarrays. So any ideas, anyone? My idea was like we can first directly count length 1 subarrays. Notice that we will not be able to do any operations here. Like if that array is 1, that will remain 1. If that array is 0, that will remain 0. So we can directly count number of length 1 subarrays, which is count of 1. Now we can also directly count length 2 subarrays. Here if both the elements are 0, it's false. If we have 0, 1, 1, 0, then also the answer is no. And then we have 1, 1. In that case, we will count it. So we can run one for loop to directly count length 1 and 2 subarrays. Now I will focus more on arrays of length greater than or equal to 3. The first critical observation was if we have AL to R, and if we can do an operation on this one, in this range, like then there should either there either two consecutive 1 and 1 should appear, or 1, 0, 1 should be a part of it. The idea is like pigeonhole principle. Like let's say we are looking at this is the length, right? Let's say this is 11, and we know that number of 1 plus 0 is 11, and number of ones are more than 0. So you can see like the number of values we can have for 0 can be either 0, 1, 2 up to 500. And if you look at it like this, let's see where all zeros are placed. Let's say there are some places, and then at some places zeros are placed. And if any place contains at least 2 blocks, then you can just start taking elements like this. Choose these 3, make everything equal to 0, everything equal to 1. Now choose 1, 1 and these 3 and make everything equal to 0. Like basically the idea is if we have 1, 1 and then something like that, then we can in fact make everything equal to 1. The idea would be choose this. Now whatever the case is, everything here can be made 1. Now in the next step, choose this one. Irrespective of what is here, you can now make everything equal to 1 because number of ones should always be high. Now we can make, similarly we can go for this side also. So if like, so that was my idea. Like if there exists any two consecutive ones, we can make everything equal to 1. Similarly, we can even do for 1, 0, 1 as well. The idea would be to first choose this subarray, make everything equal to 1, and now the problem is same as before. Now you can keep taking elements like this. So this is the main idea. And like idea was like in any range, if you can do an operation, there would be either two consecutive ones or two consecutive 1, 0, 1, because they are the smallest element where you can do any operations. Like for example, if you have 5 elements, 1, 2, 3, 4, 5. Now there can be at most 2 zeros. And to not have 1, 1 together with them, you will have to put it like this. But even in that array like this, you will be able to find 1, 0, 1 here. Or another way to see is like you will always need two zeros together, some space, 0, 0 space, 0, 0 space. Like only in the array like this, you can make ones here. You cannot make anything equal to 1 here. And in the cases of like this, for example, like this grows very fast. This needs two zeros, two ones. This needs 4 zeros and 3 ones. This needs 6 zeros and 4 ones. Like for every additional one, you will need more than 2 ones here, and that is the idea. You won't be able to. This was the main idea I had for this problem. Now the problem remains, how do we count these subarrays? The idea is like you can fix the left element. Let's say you iterate from left equal to 1 to n. Now you have some AL with you and some elements are there. And let's also mark the places where 1, 1 appears. Like let's say for example, this 1 and 1 appears. Or my idea would be like, let's keep checking this subarray. There would be some place up till which there is no 1, 0, 1 and no 1, 1. And there would be a time when this would be the first time when either a 1, 0, 1 appears or a 1, 1 appears. And anything you take beyond this point, you will always be able to make everything good, because we know that if our array contains 1, 0, 1 or our array contains 1, 1, then we are good there. And like this was the main idea for this problem. Like you can separately count arrays of length 0, arrays of length 1, arrays of length 2. And for everything greater than equal to 3, you definitely need 1, 0, 1 or 1, 1. So you can either binary search or you can do a lot of stuff here, like probably 2 pointer, etc., whatever you want, to find the first time when 1, 1 or 1, 0, 1 appears, and then you can call it again. Or like the way for 2 point, like the idea would be to maintain the positions where an array like this comes up. And this was my idea for this problem. Like length 0 would be number of ones here. lines 1, line 2. Or probably we can start from L from backward. Now, if we have at least two elements, if we have at least two ones in this ring, then we can say R is minimum of R comma L plus. Because like we know that whenever if we include L plus 2th element, then AL plus 1 and AL plus 2 would be a good subarray. Or we can also check if AL and AL plus 2 also gives us some greater benefit. Like R is the first index. Then like now we know that from index R up to n minus 1, we can make everything equal to 0. So n plus equal to n minus R plus 1. N minus R basically. Because you can choose R, but you cannot choose n. So R from R to up to n minus 1. And I do L minus minus, and whatever remains here, it looks like I have to ignore subarray 2, right? L plus 1, L plus 2's minimum to 1 second. Let's just start from L equal to n plus 2. This ends up being the solution for this problem. Okay, I don't understand. Does it not work for all cases if n greater than equal to 20? Is it contains 101 or 11? Then we can make all. Yeah, that's the main idea. So for example, 1 000 000 11 000. Can we not make all elements 1? Yes, we can make all elements 1 in that. Like, that is the idea. Like if there are two nearby ones, or if 101 is there somewhere, then you will be able to make everything equal. And that's what I am counting. Like I am finding the minimum index R such that AL to R contains that. And the idea would be whenever we move reduce left, we have to just check 3 elements next or 2 elements next to see if we can reduce our lower bound. Any questions on this problem before we move on to the next problem? I think I will discuss tree count easy and hard first, and then I will go for tree cursor. And like these are the two more problems I want to discuss. I will probably assume no questions, and then let's move to final one. This is an easy version. Like basically, we are for an array B contains m distinct integer. Say B1 to Bm, we define f of B to be the number of distinct x such that following condition is satisfied. X is greater than or equal to 1, and there exists some index ij that such that it is possible to form a degenerate triangle with side BI, BJ, and X. A non-degenerate triangle is the one with positive area. And you are given an array containing n distinct integers, find f of n. So the question here is like, first thing first, what is degenerate triangle and how can we verify if we have a degenerate? The problem statement says degenerate triangle is a triangle which contains a positive area. So for example, you can technically have a triangle like this. This is one side. This is another side of angle 0. Like, and then there is a point here, and this is another side of angle 0. So this angle is 180 degrees, this angle is 0, this angle is 0. So this is not a triangle. Similarly, basically, but something like this is a triangle and it is in fact a degenerate triangle. So the main observation question is like, can you form a triangle to begin with? And that is what the problem asked. So the idea here is like, let's say this is the largest side and these are the other two sides here. If they cannot reach here, then also it's not possible to have a triangle. So the sufficient condition is, let's say we have three sides, L1 less than equal to L2 less than equal to. Then if L1 plus L2 is greater than L3, then the answer is yes. And that is the necessary and sufficient condition. If we have three sides, maximum of the three sides should be more than the sum of remaining two sides. This is necessary and sufficient condition. The way you see is, let's say this is L3 line. Now you will have, let's draw a circle with side length L1. This will be here, something like this, because L3 is the largest side. And similarly, this is a triangle of length 1. Let's also draw a circle of radius L2 here. Then you can potentially see this point, and this point will have whatever radius we need here. This is L1, this is L2, this is L3, and we got over here. And like that is the main idea. So now if you have B1, let's say we have some BI, BJ. How can you find what all valid X are there? The idea is either X is like this side, and we have some BI here, length BI here, and some BJ here. In that case, like BI plus BJ should be greater than X, and X should be greater than BI comma BJ. So this gives us the range. We can take anything from max of BI comma BJ up to BI plus BJ minus 1. Now the another idea is like X is between, let's say, BJ and BI. This can be one case, or this can be the another case. Let's assume that BI is greater than equal to BJ. We can always take the maximum one. In both of these scenarios, we will have X plus BI should be greater than equal to BJ, should be greater than BJ, which says X should be greater than BJ minus BI, which gives us that X should be in range from BJ minus BI plus 1 up to whatever the max was. And you see like this endpoint also had a max here. So essentially our condition reduces to, for some x and j, the range of x is bj minus br plus 1 up to bj plus br minus 1. This is the fixed rate. And the idea here was for like these are the value ranges. Now let's say we have some bj like this. What is the minimum value we can have over here? The minimum we will have, like let's say our array is sorted like this, b1. We can always sort because we have to just find it for listing arrays. Some bi here, some element, some bj here, and some element, some bi here. Now the idea is like this value would be minimum only when I is equal to j minus 1. Otherwise, you see like whenever you go to, you keep decreasing bi, this value keeps increasing it. So the minimum x you can have with this as bj will always be by taking I equal to j minus 1. And similarly, because we had bi greater than equal to bj, right? The maximum value you can always have would always be when you choose this as other element. So this gives us an idea. Like let's sort all the elements. Now let's just find the range of all the x we can have for every two consecutive elements, and then count how many different x are there in that complete range and print that count. That was the main solution we had. Like counting the union of length of all the segments can probably be done. Like you can probably find it already on the problem set. Or the idea is let's look at it as a number line here. Some bj would give us this range. Some bj would give us this range. So we can just store all these segments first, and then we can probably sort them to find all the ranges here. Or there are some ways to do it with some prefix sum as well. The idea is put it in a map. You say you for each element, you count the number of segments it covers, plus 1 here, so minus 1 here, plus 1 here, minus 1 here, and you can have things like this, and then take prefix sum in this time segment, and whatever elements have value more than 0 would be the required error. So this was the idea for triangle one. Easy problem first. Yeah, union of interval code, yeah, that you can probably do over here. So the idea was take all the elements as input, sort them. Now L1, L2, like you just need nearby elements. The minimum x you can have would be L2 minus L1 plus 1. The maximum x you can have is L2 plus L1 minus x. Then my idea was let's look at this as a number line. We say the number of segment which starts from after L count has been increased by 1, and after R plus 1 the count has again decreased. Now we keep processing it. We also maintain previous element and what was the count for the previous element. So if that count is greater than 0, then anything up to previous to x minus 1 would be covered by. And you can just keep counting it and print all the unions. This was the idea for easy version. Any questions on the easy version before we move on to the hard version? For the hard version, the problem statement says we have to compute this for every prefix of array. So we cannot directly sort the computer. And my idea is again the same. We can just maintain those segments of interval again with us. And whenever we iterate, whenever we get some x, we look at what is the element just greater than current x, what is the element just less than current x, and we just add values, whatever ranges these two adds over there. Like for example, let's say I have some black box which takes range from which takes to element L1 R1, finds ranges due to it, and adds it to some data structure we have. We don't really need, I did not needed a more here. The idea was like we keep all the points here, we insert A0 first, and then we can keep inserting A1 up to A enter. Our current element is K. Find the element just more than K in the segment, which you can find out using lower bound. Now you say add two elements, L1 and L2, with current is less than current 2. Add whatever ranges due to it to your current answer. If this is not the element, then there is one element less than current element as well. So add range due to that just less than current element in also in the range and current over. And whatever union of all the segments here so far, you put it into current count here. To do this, like what I ended up doing was some interval handling. So like essentially what we can do is like we can maintain a map where we can maintain sorted list of L comma R in the ranges we want. So my idea would be like remove first I have a method remove segments. L comma R and split first split any segment which overlaps L comma R, and then remove all the segments inside L comma R, and then you add just one range L to R over here. And the idea is whenever you are removing doing something, you can also maintain the count of elements here. So I have this count which maintains total global count of all the elements I have, length of sum of all the elements and all the ranges as well. You can probably also use a set here. You don't really need a map here. Whenever you add AL to R, like you say like this is just pair of pairs sorted and kind of two like no L to R's are intersecting here. And add first, let's look at remove count here. Like it says remove all the elements which intersect with L to R. So first I look at lower bound, like all the segments which end after L. And if that second is was greater than equal to R, then the idea would be to split these segments here. Like first this is splitting some X, L and some Y was there. So the idea was to split it into two segments. X up to L minus 1 and L up to Y. And just some just not sure why. So like the idea was to just look at the interval after it. Now we can skip this interval and we can go further. As long as our complete segment or as long as any segments which ends before R is there. If that segment is completely inside that, like this is the split operation again. Now we have some L here. Let's say some X is there, some R is there, and some Y is there. In this case, we split this segment into again L to R and then remove L to R and R plus 1. So R plus 1, this segment remains and we remove whatever segment we have. And if everything is between L to R, so like L is here, then you have this X, then Y, then R. Then you can just completely remove this segment. So here I am removing the segments and I am maintaining like removed count, like number of elements I have removed. So from total points, these are the points I have removed. Now, so what I am doing is first I am removing everything which overlaps with L to R so that no element from L to R is there. And then I add a segment L to R with whatever. This ends up giving me the complete segment points here. So by the way, there are two problems in fact. Like I think this was the template by Ashish Gupta. So you can probably try out coding similar stuff on these two problems. And essentially, this was the only difficulty in the hard version here. Yeah, earlier we just sorted it, we maintained it, we can do it with complete array. Now we have to iteratively add some ranges and also keep all the distinct ranges with us and union of those ranges. Any questions on any triangle count, easy, hard, before we move on to the last problem for today? So, further, I'm curious, was min max path okay? Contest was stupid. Some people found it. Okay, I will move on to the last problem for today. It says you are given a tree with n vertices. Initialize a variable x. You would like to perform following operation and dimension. Delete the edge L to R. Let size u denotes the size of connected component that u is contained in. Size u denotes the size of connected component that v is in. XOR variable x with either the size of u or size of u. More formally this. Do any one of the following. Find the minimum possible value of x that can be achieved after performing all n minus 1. Additionally, provide a valid sequence of operations that achieves this minimum value of x. If there are multiple sequences of operations that achieves minimum, you can output any of them. So the problem statement is, let's just create a tree to see how things are happening. Let's say we have a tree like this. We can choose one of the edge first. Let's say this is the edge we want to choose. And we have a variable x equal to 0 first. Now we have two sets here. This. We can look at size of any one in this case. In this case, both are 3, so we don't really have a choice. XOR that size with x. So x0 XOR 3 would give us 3. So now updated value of x is 3. And now you have also deleted this set. Now let's say you choose this segment. Now you have size 2 here. Like basically, let's say you choose this set. Now this is one of the segment here. This is another segment here. Size here is 2, size here is 1. Let's just say, let's keep the size 2 here. So do XOR with 2 and you will get 2 XOR 3 would be 1. So now your updated x is 1. This edge has been removed from our. Now we can also remove this case, do XOR with 1, we will get now x equal to 0. Now we can remove this edge, let's say do XOR with this one this time, this 2 this time, we will get x XOR 2 as now x would be 2 here, where we would choose this segment. Now you can also delete this range, you will get 1 segment size, you do XOR with x and you will end up with x equal. So one scenario I saw, like the final value you would get with your variable when you deleted all the edges is x equal. So the problem asks us to find what would be the minimum value if we do it optimally, and then some sequence of operations to do it. So any questions on the problem statement before we jump on to the solution for this problem? Okay, the first idea I have would be, let's draw this tree first. Let's go one. My idea is always choose a leaf node and detach it from the tree. And choose the connected component of that. So for example, first delete this. You do XOR with 1. Then you have this leaf. Remove this edge and do XOR due to size of this. This removes XOR due to size of this. Now let's look at this leaf. Remove this edge, do XOR with 1. 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 If you always delete a tree, if you always delete an edge with that leaf, then one of the connected component must always have size 1. So you will have some number of x would be equal to 1 XOR 1 XOR 1 XOR 1 and so on. So this value can either be 0 or 1. And this says that the answer can never be more than 1 to begin with. Our best case scenario would be like, can we get 0? If we cannot get 0, just print 1. And the idea here was always choose a leaf node, delete an edge with that leaf node, and choose the connected component of leaf node. So you always do XOR with 1. So like this is the first idea when like if you have even number of edges, then you will do XOR even number of times, you will get 0. If you have odd number of edges, you will do XOR with 1 and you will get an odd one. So that is the first iteration. Now we know that if n is odd, we will do XOR even times and the x is 0. If n is even, the answer is either 0 or 1. We are yet to find out like can we get 0, and if we can get 0 then in what cases. If we cannot get 0, then the answer is 1. Then here the idea was like, let's look at this graph 1, 2, 3, 4, any component here. Like just choose any graph of size 4 and delete a leaf node from here. So this would be one leaf node and this would be some 3 nodes here. The idea is instead of choosing this component, choose this component of 3 nodes. So you will get x equal to 3. Now you will have 2 nodes 3 and now this is split and you have a graph with 3 nodes. And again there would be a leaf and there would be 2 more nodes there. The idea is again to choose the connected component of leaf 2 here. So 3 XOR 2 will become 1. And now we have 2 nodes here. Both of them are leaf, so you can split them again with 1 nodes each. And you can do a XOR here again. And 3 XOR 2 XOR 1 is 0. So what I have shown is like if we have 4 nodes which is even, our earlier algorithm of always removing the leaf and taking 1 1 will give us 1, but this way we can get a 0. And this would be my basis of idea for all the even cases. Like remove, like n is even, right? Remove 2 leaves, you will get n minus 2. And XOR would again be 0 again. Then again remove 2 leaf, you will get n minus 4 and you can keep doing it. There would be a time when you will get n equal to 4 and then use this algorithm so that your final overall XOR is 0. And this can work only if removing 2 nodes can give us 2. So n equal to even and n greater than equal to 4 can also give us x equal. We have a solution for what to do when n is odd to get XOR 0. We also know when n is even and greater than equal to 4, how we should do operations to get x equal to 0. The only case remaining is n equal to 2. In this case, the graph looks like this. Does not matter, like you don't really have a choice here. If you split this, you will get both the component of size 1. Whatever you choose, you will get x equal to 1. And that was the solution for this problem. Answer is 1 when n is equal to 2, otherwise x is always equal to 0. Just the way you do operations changes a bit based on when n is odd, when n is even. For n equal to odd, the simple solution where we always take a leaf, delete it, and keep doing it, we will do XOR even number of times and we will get 0. For even case, the idea is to remove 2 leaves in one go. And so at last you will reach up with n equal to 4 and then you can use this algorithm to get XOR 0 here. And when you remove 2 leaves, you do XOR of with 1 2 times and you will have 0 back when you reach n equal to 4. And this was the idea for this problem. Like I think I missed out. Like in contest, I was mostly trying odd even cases. I was brute forcing there. What makes me really surprised is why my brute force. Like I in fact even ran a brute force solution to find this case, but not sure where my brute force or stress testing was failing. Perfect. In contest, I was doing stress testing, but I forgot to merge components when I'm doing it. And that's why my brute force solution never gave me this counter test case. So like I was stress testing, I was not finding counter test case for small, like my stress test was asking for n equal to 4, etc. And the simple reason was like I did never merge operations, so all the components were size 1 only. And if you do size 1 components or n minus 1 times when n is 0, you will get. So, oh, what I did was like generally the way to do stress testing is, let's say you first generate a random graph. How to generate a random tree, I will come back to it later. Then you write two code. One code is your optimal solution, which is giving me the optimal, returning me the optimal value of x. And one is some brute forcing, which you are confident that will give you the correct. So my idea was to just try out all the permutations, how we are merging. Like my idea was instead of like it's a good question, like how will you write a checker? Like how will you ensure that whatever a user has printed is correct? The way would be like instead of deleting edge, you start with everything one, then you start merging edges to get the complete component. And whenever you are merging, you also know which size to take up here. So you can take XOR from there. So instead of starting x equal to 0 and breaking it, the checker would probably start from x equal to 0 and reverse all the operations and start merging the cases here. So to brute force it, what I did was like I have fixed the sequence of edges in which I want to merge. And then I have a DSU here. Like, so I look at what is current size of first component, current size of second component, put that in a vector format. Like these were the two choices you have and merge them. In my stress testing, I forgot to do this. So I always have x1 equal to 1, x2 equal to. And the idea is like now you can probably run some knapsack DB or whatever you want. And like I probably did recursive solution which tried probably a bit. You can also do some bitmask solution, whatever you want to just generate all the size. So now once you have a tree, you have a brute force solution to find what can be the optimal answer. You also have your own solution here. And like generally when you want to generate an optimal tree, this algorithm is sufficient most of the time. Like if you just for I equal to 2 to n, just generate, let's say this is for v equal to 2 to n, generate u as random number, which is between 1 and u minus 1, 1 and v minus 1, and add uvh. You can use this simple algorithm to generate a tree to win. And most of the time this is sufficient. And probably I had this like there is something known as preferred code as well. Probably you don't really need it for most of the stress testing, but I just had this code handy, so I ended up copying it from my template. So like you can also use some preferred series to generate a random tree over here. And that would be the idea to stress test here. So like now I feel sad, like I did not check my brute force code here. Like this line was missing, so I was always getting 1. And my old solution where print odd even 0 1 was also giving me right. So this is three counts now, and like I will probably mostly skip min max part. Like I did not thought about it much in the contest because I was mostly stuck here. So yeah, I think this ends up my stream for today. Any questions, anyone, before I call it a day today? Next, I am planning to do Hacker Cup stream on Saturday, so do watch out for that too. Like looks like last time there were some issues with the Hacker Cup stream, like it was not available for quite a long time. And thanks everyone for joining me. Hey, hi, Blister, yes. Is it a good idea to just a solution of problems that are way beyond my rating range now? Like just watching the solution will not help you much. You will most likely not even remember the idea, and if you don't understand the ideas, that's not helpful. The idea is to probably, like, I don't know, like this graph is just buggy. Like it just takes everything there and predicts rating. What CodeChef does is they do not change the rank list when the contest is running. After the contest, they remove people from the rank list and then calculate it. So this predictor is mostly useless for D1 people. Now I am no longer in the rank. So my rating did not decrease by the way. Yeah, it's still 7. Like yeah, like there is a chance like this predictor is not at all correct when it comes to D1. But if you are already getting negative, then I don't think you will get positive because the way you see is like most like you have a rank list and where you are getting something negative, or yeah, you it may even turn positive. Yeah, I don't really know because if you remove some people from the top, it's a good chance that your rating will increase. So if you are -5 or something, there is a chance you will get a positive delta. Because right now the contest is taking into like the way rating system mostly works is like in the chess match, you know, elo rating, right? So if there are 10 people participating in the contest, rating system considers there are 10 C2 one-on-one matches there, and then they try to increase who won, who lost, and some calculations there to increase. So if someone stronger than from you is removed from the ranked list, like there is a chance your rating may have a positive impact. Like physically stronger does not come matters when it comes to CodeChef rating. Like stronger by I mean like higher rating here. So like CodeChef rating is not Elo rating, but Code Forces has an. So you can probably reach out. So one fun fact is like tourist rating is around 4,000 on Code Forces, right? And my rating is around my rating is around 2,300, right? So a gap of 1,700. The probability that we have a match Aryan versus tourist and tourist beats Aryan is same as the probability that I beat someone with rating 600. So like probability that a 800 rated person beats me is more than probability that I can beat tourist. So just a fun factor because this is a formula which calculates probability that if a person has RB rating and a person has RA rating, what is the probability that A rates B? And do I take part in Universal Cup? No, I think I stopped long ago. Earlier, I used to do it with us. So I think this ends up stream for today. Yeah, like people who are close to tourists can definitely beat him. When it comes to small people like us, we stand no chance. Yeah, like these are at the end of the day always formulas, right? Some mathematical system, and contest takes into account what problems are there and how good you are at on those types of problems. Sometimes the problem would be in your flavor, sometimes not. Sometimes it can be the case that a person was not in good shape, like probably tourist was not in good shape, or probably that jingle is rated lower than what he is. So yeah. So I think this is for today's stream. Thanks everyone for joining today. I think I will call it a day.